everyone. We're going to continue to discuss the topic of differentiability, what makes a function differentiable. And just to remind you, there were sort of three main things that we were looking for. First of all, the graph had to be continuous, right? No breaks in the graph. Second, you couldn't have any sharp corners or sharp turns. And the reason for that is the derivatives do not approach the same value coming in from the left and the right. And since the derivative is really a limit of these slope values, if the right and the left are approaching two different things, you don't have a derivative there. And then the third one was you can't have a vertical tangent line because you can't find a slope for a vertical line. So if we're looking at this function, absolute value of x minus 2 plus 3, there's a spot where it's not differentiable, and I want to know where it is. And you could graph this and look at it, but let's suppose that you had to answer this question without using technology. You don't have a graphing calculator at your disposal. I certainly don't want to take the time to graph this thing by hand. This is where we have to rely on what we know about transformations and parent functions. This is based on the absolute value graph, right? Y equals the absolute value of x. And so the problem we have with the absolute value function is that it's got this sharp corner, right here, typically at 0, 0. That spot is not differentiable because if you were to take the slopes coming in from the right and the left, they're not the same. Okay, so it fails that item number 2 on the list of differentiability criteria. So then let's think about what this thing's going to do to that function. This x minus 2, if you remember back from all the times we've talked about transformations, is going to take that vertex point and move it 2 to the right. And this plus 3 hanging out outside of the brackets is going to shift me up by 3. Okay, so I'm going 2 to the right and 3 up. So the new coordinates of this 0, 0 based on this transformation, 0, 0 is going to translate to 2, 3. And that would be my point that's not differentiable. Honestly, most of the time all we care about is the x value. So I would say like x equals 2 is the place where we're not differentiable. And you can also kind of verify that because if you put 2 in here, you get the 0. 2 minus 2 is 0. And that's that same 0 that we started with here. Okay, that was again just to kind of, get you thinking about what we know about these functions and how transformations can help you answer these. This is going to shift gears a little bit. This is going to take us into finding derivatives with our calculator. And I'm going to try to show you two different ways. I hope my calculator will show both. But let's just talk about what we think the answer to this might be before we even touch our calculator. So we want to find the derivative of y equals 3x squared at x equals 2. Okay? This is the type of question that your calculator is really good at, is finding a derivative at a specific value. And we'll talk in a minute about how your calculator does that. But we already know the answer to this question. If f of x is equal to 3x squared, and we've talked a couple of times about how the derivative of x squared is 2x, then the derivative of 3x squared is 3 times 2x, so that's 6x. And then if I want the derivative specifically at 2, I'm going to do 6 times 2 and say the answer is 12. That's the type of derivative math we're eventually moving into. This question actually asked me to do that on my calculator, but I wanted you to be able to verify sort of by hand what the correct answer should be. So let me show you what magic your calculator can do for you. I'm going to hit the math button. Let's see, try to move this out of the glare. And under math, I'm going to slide down to option number 8, which says n-deriv. Okay? And when I choose n-deriv, this is what my calculator screen looks like. There's 3 things I have to fill in here. Your calculator screen might look different than this, and again, after I do it this way, I'm going to try to go back and show you the other way. But here are the 3 things that we need to fill in no matter what our screen looks like. First, this d over d blank here, we're going to type an x there, and that's just saying we're taking a derivative in terms of x, which, by the way, that's how I would write this out. Like if I was trying to communicate what I was doing, I would say, look at me, I'm taking a derivative of the function. So the next thing I'm going to type here in my calculator is the 3x squared function. Okay, so I'm taking a derivative of 3x squared. Now, if I was just taking that and I just wanted to say, okay, the answer is going to be 6x, I could just say equals 6x, and that notation would be fine. But if I want to say specifically at 2, I'm going to say at x equals 2, and then give an answer. So in my calculator, I'm going to go down here to where it says x equals, and I'm going to type in a 2. So I put an x here to say I'm differentiating in terms of x. Most of the time in this class, you're going to differentiate in terms of x, but just know you can do it with different variables too. There's my function, there's my value, and lo and behold, it gives me an answer of 12, which is what I expected. Okay, that's what I expected when I kind of did it by hand myself. Here's the thing I want to caution you about though. Your calculator is not very good in situations when a derivative does not exist. So let's think about one of those we just talked about. We talked about the absolute value function. So I'm going to type in the derivative of an absolute value. So I'm going to differentiate in terms of x. I'm going to go absolute value of x at x equals 0. And we talked up here about how we know that derivative does not exist because you've got a sharp pointy corner. But if I type this in my calculator is going to tell me that answer is 0. Here's why. Your calculator is not actually doing a derivative. It's doing a very, very close approximation using an average rate of change. So when I ask my calculator this question, what it actually does, it goes really, really close to 2 on either side. So it probably goes to like 1.99999 and then 2.00001. Okay? And it does a slope calculation. An average rate of change that is so close to that x value is probably going to give you a close enough slope value here to where at least with rounding you won't have an issue. Okay? And so that's what's happening here, is your calculator is going on either side of this 0, and it's picking a point here and it's picking a point here. They're really, really close to 0, but then it's doing a slope calculation between those 2 points. And what it's finding is that there's a horizontal line there, and it's telling you that the slope is 0 when actually the slope does not exist. So this line is just in here to remind you that we can't always trust our calculator. Okay? In this case, you have to be smart enough to know when a derivative exists and when it doesn't. And then one quick thing in here that I feel like we sort of already talked about, but it is officially a theorem, is if I hand you a function and I say, hey, this function is differentiable, you automatically know it has to be continuous. So differentiability implies continuity. Okay? Because you have to be continuous to be differentiable. So if I tell you a function is differentiable, it has to be continuous. Okay? That's going to be really helpful if you think about all of those theorems we've learned that only work if a function is continuous. If I hand you a function and say, here's a differentiable function, a little light bulb can go off in your brain and you can say, oh, I know that means that this thing is continuous. It does not work the other way around though. I mean, think about this example. Absolute value is continuous. It is not differentiable. So knowing that it's continuous does not automatically mean it's differentiable. There's some other criteria we have to meet. But if it's differentiable, we automatically know it's continuous. Okay, that's really it for the rest of this lesson. I hope that makes sense to you. This knowing how to do this on your calculator is going to be a big thing right now. We'll eventually get into doing it more by hand, but for right now, your calculator is your friend. Okay, have a great night.